Good afternoon, everyone. My name is Edgardo Barzallo, and I'm going to present the paper Vulcan Lessons on Reliability of Wearable through State-Aware Fuzzing. The other authors of this paper are Nirjon, Kefan Chu, Omiyamaji, and Saurabh Bachi, all from Purdue University. Here's the outline for this presentation. Let's start with our motivation. Over the last decade, wearable devices have grown in popularity. This growth has been driven primarily by fitness tracking and health monitoring use cases. And even though the reliability of mobile application is well explored, that's not the case for wearables, which poses a new set of challenges. Wearable devices are often fitted with a variety of sensors not available on mobile devices. Besides, these devices have limited resources such as reduced display screen, low computer power, and limited battery life. Due to their reduced size, wearable devices are often designed to require minimal interaction from the user, interaction which is often limited to swipes or clicks. Moreover, because of the same reason, wearables application often relies on a mobile counterpart. Since these devices are commonly used for health and fitness purposes, it is important to understand the vulnerabilities in their software architecture and how to mitigate them. Existing testing approaches are focusing on cover reliability issues related to the user interface, and even it is important for improving the user experience, it overlooks some of the important characteristics of wearables, such as inter-device communication and sensor awareness. Based on this premise, we propose Vulcan. To the best of our knowledge, Vulcan is the only testing tool for wearable apps which focuses on these types of interaction. Next, I'm going to talk about the more relevant aspect of Vulcan design. In order to force wearable application with awareness of their state, Vulcan needs to build a state model for each app during a training phase. Vulcan uses two key features of wearable to build this model: the sensor activity and their inter-device communication. The first one indicates the status of each sensor equipped in the device, while the inter-device communication denotes the presence of any ongoing synchronization between the mobile and the wearable. We will define the state of the app as a vector using these two parameters. Let's take a look with an example. Suppose we have a fitness application in a device with only two sensors, heart rate and a GPS. Therefore, the state of the app will be defined by a vector with three variables. The first one corresponds to the communication, while the other two to the state of each of the sensors. This finite state machine represents the state model of the application. As we can see, in the initial state, all the variables are in zero. When the user decides to start the workout, a message will be sent from the mobile to the wearable device. Then, the sensor will be activated. The user will start her workout. When the user decides to finalize her workout, both sensors will be deactivated and everything will finalize with a message sent from the wearable to the mobile device. A key part of our state model is the concept of vulnerable state. We define the vulnerable state of a given app as the state with the maximum concurrent activity observed during the training runs. The underlying hypothesis is that by fuzzing the app in its vulnerable states, we can discover more bugs in a shorter time. Let's explore Vulcan Workflow. Vulcan works in two phases. In the offline training phase, the tool learns the finite state machine model of the app. At first, a UI testing tool is used to explore different possible UI interactions that a user might have with the target app during a normal use. In the process, Vulcan collects logs that will be parsed later to build the state model. We adopt the robot UI testing tool and run it until a time threshold. Then we terminate the training process to parse the collected logs to build the state model that represents the application. During the online phase, the traces are used to steer the app to one or more vulnerable states, denoted by the degree of concurrency. Then a sequence of semi-valid intent and communication messages, depending on the state, are injected into the target application, which lead to a higher fault activation rate and even system reboots. Vulcan has two main fuzzing strategies. The first one, the intent injection fuzzing, and this is applied for the intra-device communication. Let's recall that intent are used in Android in order to communicate process between the device. So here, depending on how we force the value of the intent, we can have an empty campaign, a random campaign, or a semi-valid campaign. In the first one, in the empty, basically we are nullifying the values of the intent. In the random campaign, what we are doing, it's like we're generating random values for each of the fields. And finally, for the semi-valid, what we do, it's like we generate valid values for each of the fields, but basically the combination of these fields, it's not valid. For example, let's look to the one that we have in this slide. Basically what we did, it's like the combination of the action fitness track, it's not valid with that component. The second fuzzing strategy is the communication fuzzing, and this one is applied to fuzz the communication that happens between the wearable and the mobile device, the inter-device communication. Here we can distinguish two types of campaign depending on how we fuzz the message that is sent from one device to another. We can either have an empty campaign or a random campaign. The last one, we basically generate random bytes in the message. Vulcan decide which fuzzing strategy applies depending on the state of the app. For example, if the app is in a vulnerable state that has ongoing synchronization, Vulcan is going to use the communication fuzzing. Otherwise, it's going to use the intent injection one. To maximize the effectiveness of our semi-valid intent injection campaign, we wanted to generate the intents following the Android specification. In preliminary experiments, we found that most of the intent that we generated randomly were discarded by the Android runtime. This motivates us to intelligently generate intent by combining only the valid fields instead of just randomize the values of 40 fields. Therefore, we built a text analysis tools that basically parse the Android specification that it's available publicly in the web. This text analysis tool then generates a JSON file that it uses as an input for Vulcan in order to generate the semi-valid intents. In order to parse the Android specification, we mainly rely on two core analysis techniques, the lexical matching and the pattern matching. Basically, with this feature, not only Vulcan can generate intents following the specification, but we also can adapt to the change in the Android intent specification. Now, I will talk about the results of our state-aware study. We evaluated 100 applications and sent over 1 million intents. We compare Vulcan against state-of-the-art testing tools. Ape, a stateful testing tool that builds a model based on the UI interface of the application. A QEA, a state-agnostic tool that uses an intent injection campaign that basically randomizes the value of the intent. Monkey, the de facto testing tool that was developed by Google. We designed our experiment based on the following goals. First, we evaluate the effectiveness of our approach against a state-agnostic strategy. For the second one, we wanted to evaluate the impact of the degree of concurrency on the overall reliability of the application. Here, we hypothesize that altering the global state of the device, that means how many and which sensors are activated, we can lead to different failure manifestations. In order to accomplish this, we built an external application that we call the Manipulator app. The Manipulator app basically stresses the wearable device itself by creating contention from various sensors. Here we have two different cases. We either activate the same sensor that were activated by the target application, or we activate the complement of those sensors. Let's discuss our results. For our experiment, we focus on three failure manifestations. The first one is when the target application crashes. The second one is when the target application does not respond. And finally, the third one, and the most severe, is when the device reboots. As we can see here, Vulcan was able to trigger more crashes and more system reboot than any of the others testing tool. And in fact, Vulcan was the only testing tool that was able to trigger system reboot. This can be explained in the fact that Vulcan can steer the application to a state where it's more vulnerable. Also, let's take a look to this table. As we recall, our second goal for the experiment was to evaluate the effect or the impact of the degree of concurrency and the reliability. Here for experiment 2, we're using the Manipulator app in order to activate the same sensors that are being activated by the target application. By doing this, we are creating resource contention that it's leading to more ANR and more system reboots, meaning that the sensor activation at the end has a negative effect on the overall reliability of the system, and also the degree of concurrency is affecting the overall reliability of the application. Now let's take a look to the distribution of deception that causes the application to crash. As we can see here, null pointer exception is the main cause of failure across all the testing tools, and this is consistent with prior work in Android and Wear OS. Let's remember that this type of crashes can be easily avoided by doing exception handling in the apps. Now let's focus on the unique crashes across all the testing tools. Here we have the monkey was able to trigger 9 unique crashes that none of the other tools were able to trigger. In the case of ape, the number is 12, QEA is 3, and finally Vulcan is 8. Some number that pop-ups here is the fact that Vulcan and QEA has a large overlap, and this mainly can be explained in the fact that both tools use an intent injection campaign. Neither of the other tools use intents in order to force the target application. But some of the main difference is that Vulcan uses a state-aware strategy where basically QEA just randomly generates intent in any without any awareness of the state. Also, the intents that are generated by Vulcan semi-violent are more closely related to the Android specification. Let's keep comparing QEA and Vulcan. In terms of efficiency, Vulcan is 5 times more efficient than QEA, meaning that Vulcan requires less intent in order to trigger the same number of unique crashes than QEA. This is explained in the fact that the intent generated by Vulcan are most closely related to the Android specification. In the case of QEA, those intents are mostly random generated. Also, Vulcan generates less duplicates intents, and finally the intents generated by QEA are rejected by the Android runtime at a higher rate. In the case of the failure types, Vulcan was able to generate failures related to inter-device communication. That is something that is not possible to do in QEA. Finally, in regards to the system reboots, in our experiment, QEA did not trigger any system reboots at all. Actually, Vulcan was the only tool that was able to trigger system reboots. Something that we found is like application that has a high degree of concurrency often trigger system reboots. And this degree of concurrency is denoted by the number of sensors that are activated. In this case, Vulcan was able to trigger system reboots deterministically with these apps. Next, I will talk about our analysis regarding system reboots. In our results, we show that it's possible to trigger system reboots on Wear OS without any system level or root privilege. Basically, one application in user space can make the device soft reboot just using intent injection. These system reboots were mainly because of resource starvation, and this resource starvation was related to a high degree of concurrency denoted by the sensors that were activated in the device. Next, we have the watchdog, that it's a protection mechanism to prevent the wearable from becoming unresponsive. We found that the root cause of the system reboots is related to log handling in the OS. Basically, this watchdog it's constantly monitoring all the threads that are part of the system server. If for some reason one of these components that is being monitored by the watchdog gets harmed because it cannot acquire one of the logs, the watchdog will kill the whole system process. By killing the system process, it's triggering a system reboots in the device. To mitigate these system reboots, we designed a proof of concept solution based on an intent buffer that will alleviate the resource starvation in the device. Since Wear OS is closed sourced, we implemented our solution in application level. Every intent that is sent from one application to another, it's first stored in a buffer, and then we will have a fetcher process that will fetch one intent at a time. Any system intent or trusted intent can bypass our solution. We tested our solution against an intent injection attack, and our proof of concept solution was able to mitigate the system reboots. Moreover, to evaluate the effect of our solution in the user experience, we conducted a user study with 15 users, and only one noted a significant difference in the performance of the latency introduced by the intent feature. Next, let's discuss the lesson learned from this state-aware study. First, we have the improper input validation of intent is still a major cause of crashes in Wear OS. Also, we found that legacy code found in Wear OS, a code that is being shared with Android OS, makes the wearable application vulnerable to an injection of key code search in the device. Also, we found vulnerabilities related to the ongoing synchronization between the mobile device and the wearable device. In this case, for example, if one wearable application crashes, this error can be propagated to the mobile application, making the mobile application crash. And finally, Wear OS is vulnerable to system reboots due to resource starvation. And now our conclusions. We show that state-aware fuzzing leads to more app crashes compared to a state-agnostic fuzzing. We also show that it's possible to deterministically reboot a wearable device from a user app without any system level or root privilege, just by targeting a vulnerable state. And besides, our proof of concept solution based on the intent buffer help to prevent these cases. Thank you.